again, time for another test to see if an infinite series converges or diverges. This time it's the ratio test. At the end of this lesson, you'll be able to determine whether an infinite series converges or diverges using the ratio test. All right, first of all, when should I use the ratio test? The ratio test is very nice to use when you have fractions and when you have factorials. They're also nice to use. So if you see either of those and you're not sure what test to use, the ratio test is usually a good one to use. All right, what we are going to be doing, if we have the series a sub n, it has positive terms, what we are going to be finding is the limit as n approaches infinity of a sub n plus 1 over a sub n, and we're going to find out that it's going to equal some number. Okay, we'll call that number p. Right? If p is less than 1, the series will converge. If p is bigger than 1 or infinite, the series will diverge, and unfortunately if p does equal 1, the test will be inconclusive. That won't happen very often, but if it does, we will just have to try another test. Alrighty, one thing I do want to remind you of when we have factorials, remember factorial, like if it's 5 factorial, that just means 5 times 4 times 3 times 2 times 1. So if you see a factorial, that's at least what it will be. So let's go ahead and dive into an example. Is the series n equal 1 to infinity of n squared e to the negative n convergent or divergent? Excuse me, you'll notice on this one, it's not a fraction. So I'm actually going to make this one a fraction, because no matter what test I use, that's usually the easiest way to start it. All right, if I were to try the nth term test on this one, I'd get an answer of 0, so this would be inconclusive. If I were going to try any other test, really the only other test that would probably be appropriate would be the integral test, and I'd have to use integration by parts, which might take me a little while. So the ratio test is actually a perfect one to use because of the powers. So what we're going to be doing, a sub n, please remember, is n squared over e to the n. So a sub n plus 1 is just going to be, we're going to add 1 to each n. So this is going to be n plus 1 squared over e to the n plus 1. That's all there is to it. So now what we're going to do, if I use the ratio test, and we'll always let our reader know what test we're doing, we'll be finding the limit as n approaches infinity of n plus 1 squared over e to the n plus 1 divided by a sub n, which is n squared over e to the n. So we're going to multiply by the reciprocal, and that will be e to the n over n squared. And then if I were to do that, if I have e to the n over e to the n plus 1, I'm just going to come over and show you a little side trip on this one. E to the n plus 1 is really e to the n times e to the 1, and the e to the n's cancel out, so I'm just left with 1 over e. So the n part cancels out, so I'm left with, when I do that, I'm left with n plus 1 squared over e n squared. And then from here, if I were to plug infinity into the numerator and the denominator, I get infinity over infinity, which allows me to use L'Hopital's. So we'll be finding the limit as n approaches infinity of the derivative of this, which would be, we could do a u squared. The derivative of n plus 1 squared or u squared would be 2u times du. Well, du is going to be 1 in this case, so it's just 2 times the quantity n plus 1. And then the denominator, please remember that e is a constant, so if I take the derivative of n squared, I'll just get 2n, so this will be 2en, my 2's cancel, so I'm left with n plus 1 over en. If I plug in infinity, again, I'm going to get infinity over infinity. So once again, time for L'Hopital's. So I'll get the limit as n approaches infinity. Let's see, the derivative of n plus 1 is 1, the derivative of en is e, and 1 over e is my answer. So 1 over e, if you can think of 1 over, this would really be like 1 over 2.7 something, and 1 over 2.7 something is definitely less than 1. So since p is less than 1, we can say that series is going to diverge. We can say the series n equals 1 to infinity of n squared e to the negative n converges, and that is due to the ratio test. All right, let's try another one. Is the series n equal 1 to infinity of n factorial over 10 to the n convergent or divergent? Right, as soon as you see a factorial, ratio test is the way to go. So we'll do a sub n is equal to n factorial over 10 to the n, which means a to the n plus 1 is equal to n plus 1 factorial over 10 to the n plus 1. All right, so now we're ready to use the ratio test. Okay, we'll find the limit as n approaches infinity of a sub n plus 1 over a sub n. And once again, we will be multiplying by that reciprocal, so I'll get 10 to the n over n factorial. All right, on this one, we've already found out when we did the E1 in the previous example that n's actually cancel out, so I'm just left with 10 in the denominator. So I have n plus 1 factorial over 10 n factorial. All right, now you might be wondering what's going on with these factorials. Let's figure it out. N plus 1 factorial means n plus 1, and then go down. So if I subtract 1 from n plus 1, I'll be at n. And then if I subtract 1 again, I'll be n minus 1, n minus 2, dot, dot, dot. Okay, in the bottom, I have a 10. Now, n factorial means n times n minus 1 times n minus 2, dot, dot, dot. So notice, all of those terms are going to cancel out, so I'm just going to be left with the limit as n approaches infinity of n plus 1 over 10. And if I plug infinity, I will get infinity. So since my p is greater than 1 or infinity, we know that this series is going to diverge. So I will just say since p is greater than 1 or infinite, then we know the series n equals 1 to infinity of n factorial over 10 to the n will diverge. And there we go. So hopefully now you are familiar with using the ratio test.